Hello, welcome back. In this video we'll discuss the electron microscopes, namely the scanning electron microscope, that is SEM, and the transmission electron microscope. A microscope is an optical instrument used to magnify the small objects. The magnification of the microscope depends very much on the wavelength that is being used to view the objects. Typically, the optical microscopes, they can magnify to an extent of 1000x. When you use the ultraviolet light, the magnification can be improved to 2000x. But the same instrument cannot be used to operate at UV. Reason being, the material characteristics of the lenses, they differ from the visible region to the UV. As a consequence, we have to modify the structure of the microscope itself. But we are getting a twofold increase in the magnification. The reason being, we are decreasing the wavelength from say 500 nanometers to say 400 nanometers to achieve this kind of a magnification, which means if we can reduce the wavelength of the light that is being used, then we are going to achieve a higher magnification for the same microscope. But in the electromagnetic spectrum, beyond UV, we have certain limitations to produce the electromagnetic waves. To achieve a higher magnifications, we employ the de Broglie waves. What are de Broglie waves? De Broglie waves are the matter waves. So when you use the de Broglie waves or the matter waves of the electrons, then we can achieve a significant improvement in the magnification. One can even achieve 10 power 6 x or 10 power 7x magnification. Electrons are being used in microscopes, namely the electron microscopes. Reason being, electrons have charge and hence can be deflected using magnetic field. We know that the electrons that are moving along certain path can be deflected by using an external magnetic field. We make use of this principle to develop the magnetic lenses. These magnetic lenses are used in the electron microscopes. Since the image produced by the electrons cannot directly be seen, we use fluorescent screens. Since the image produced by the electrons cannot be seen directly with naked eyes, we use a fluorescent screen. The image produced by the beam of electrons will be only in the variations of the number of electrons hitting certain area across certain cross section. Since we cannot see the electrons directly, we use the fluorescent screen to see the effect of the number of electrons hitting on the screen at various locations on the screen. Thereby, it generates the image. So the image can be seen on the fluorescent screen. In our syllabus, we have two different microscopes. The first one is a transmission electron microscope, and the second one is scanning electron microscope. The transmission electron microscope is the first electron microscope to be developed, and it works exactly on the same principle of light transmission microscope. The TEM works similar to a light transmission microscope. But there is one striking difference. The difference is, in the case of TEM, we use electrons, while in the case of light transmission microscope, we use light. Now we shall discuss the construction of a TEM. The schematic diagram of a TEM is given here. Since it is an electron microscope, we need to have an electron source or an electron gun. The construction of the TEM starts with an electron gun. What this electron gun does is, it produces the electrons or it emits the electrons. But the emitted electrons will have small kinetic energy, thereby they are likely to have longer wavelengths, because the de Broglie wavelengths suggest that higher the momentum, shorter will be the wavelength. Because we know that from the de Broglie, lambda is equal to h by mv. So when the momentum is large, we are likely to get a shorter wavelength. When the momentum is high, we also see that the kinetic energy of the electrons, that is also going to be high. We have to improve the kinetic energy of the electrons emitted by the electron gun. To improve the kinetic energy of the electrons, we have an anode here. This anode accelerates the electrons. When the electrons are accelerated, they achieve higher kinetic energy, thereby we'll get shorter wavelengths for the electrons. In fact, this structure is similar to a cathode ray tube. The TEM structure similar to a CRT, cathode ray tube. Structurally, these two are similar. The TEM consists of a number of magnetic lenses. In this example, we have the condenser lens, we have the objective lens, intermediate lens, and the projector lens. We have a number of magnetic lenses in the path of the electrons and a fluorescent screen to produce the image. What are these magnetic lenses? The magnetic lenses are solenoids encased in soft iron and has soft iron pole pieces to concentrate the magnetic field lines. We have a number of magnetic lenses in a TEM, and these magnetic lenses are essentially solenoids that are encased in soft iron and has soft iron pole pieces to concentrate the magnetic field lines. The focal length of these magnetic lenses will be about few millimeters. However, the focal length can be varied by changing the current through the magnetic lenses, because when the current is increased, the field strength also increases. Similarly, when you reduce the current, the field strength also comes down. Focal length of the magnetic lenses will be about few millimeters. Now we shall see the working. Since we have an electron gun, when it is biased, it emits the electrons. So the electrons are emitted by a hot cathode, and these electrons are accelerated to high velocities with the help of an anode held at 50 to 100 kilovolts. So electron gun emits the electrons. They are accelerated by 50 to 100 kV potential difference between the cathode and the anode. The electrons pass through a magnetic lens that acts as a condenser lens. The first lens is the condenser lens. What this condenser lens does is, it produces a parallel beam of the electrons. So the electrons are emitted by the gun, that is the cathode, and after this, these electrons, they pass through the specimen. The electron beam passes through the specimen or sample. Thickness of the sample should be about 100 to 1000 angstroms. This is the thickness of the specimen or sample. Why should it be so thin? Reason is, if it is not thin, then the electrons are likely to undergo scattering. When the electrons they scatter, we will not be able to get the desired image. So we take a very thin slice of the specimen. We'll insert the specimen in the microscope after the condenser lens. The beam of electrons, they fall on the specimen and they penetrate through the specimen because it is very thin. After passing through the specimen, the electron beam goes through a second lens which acts as the objective lens and forms an intermediate image. After passing through the specimen, the electrons then they pass through a second lens, and this forms the intermediate image. And the second lens acts as an objective lens. After that, the beam passes through a third lens that acts as the eyepiece, means objective lens. Then it passes through the third lens which acts as eyepiece. And this lens forms the final image of the object on a fluorescent screen. The fluorescent screen converts the image into an equivalent optical image. The resolving power of an electron microscope will be of the order of power of TEM, will be 10 to 100 angstroms. So such a great resolution power one can achieve. The magnification will be of 10 power 7x. Now we shall discuss the scanning electron microscope. for short is called as SEM. The schematic diagram of the SEM looks like this. In SEM you have a vacuum chamber. Within that you have an electron gun. The electron gun emits the electrons that are accelerated. We have the condenser lens. We have the scan coils. The condenser lens produces a fine beam of electrons. The fine beam of electrons passes through the scan coils, and these scan coils are driven by the scan generator. Depending on the voltage applied to the scan coils, the electron beam will move back and forth. That is the purpose of the scan coils. The scan coils, they can deflect the electron beam back and forth. As a result, the sample that is placed here will be scanned by the electron beam. After the scan coils, we have the objective lens. This is the objective lens. Electrons that are incident on the sample surface, they generate the secondary electrons. These secondary electrons are collected by the electron collector. The electron collector produces an electrical signal. The signal is amplified using an amplifier. The amplified signal is fed to a CRT, that is a cathode ray tube display or a camera. This CRT will display the image of the sample in the magnified version. The scan generator also receives signal from the CRT. Construction. We have the electron gun to emit electrons, anode to accelerate electrons, condenser lens to produce fine beam of electrons, scan coils to move the beam back and forth, scan generator to supply power to the coils, objective lens to focus the electron beam on the sample. Electron collector collects the secondary electrons, amplifier to amplify the signal, CRT display to produce optical image. Now we shall look at the working. The electron gun generates the electrons, and these electrons are accelerated by an anode, and the beam is made into a fine beam by using a condenser lens. This fine beam of electrons will be made to move back and forth by the scan coils that are driven by the scan generator in synchronization with the CRT display. And we have the objective lens. This objective lens focuses the electron beam on the sample. The beam, after hitting the sample, generates the secondary electrons, and the secondary electrons are collected by the electron collector, and we have the amplifier that amplifies the signal, and again it is connected to the CRT to display the magnified image of the sample surface. The entire setup is enclosed in a vacuum chamber, and the purpose of the vacuum chamber is to prevent scattering of the electrons with the atoms or molecules in the air. In this video, we have started our discussion by stating that the shorter wavelengths of light can produce a greater magnification. The key principle to improve the magnification is to reduce the wavelength or to make the wavelength shorter. We have seen how UV light can generate 2000x amplification, and using the matter waves of the electrons, one can produce magnifications up to 10 power 6x or 10 power 7x magnification is possible. Using the matter waves, one can achieve 10 power 6 or 10 power 7x magnification. The electron microscope consists of several magnetic lenses, and the magnetic lens is nothing but a solenoid, because the beam of electrons can be deflected using a magnetic field. We use magnetic coils or solenoids as lenses in the case of electron microscopes. The transmission electron microscope is the first electron microscope to be developed, and it works exactly on the same principles of light transmission microscope, except for the difference that in the place of light we'll have the electron beam that is used in TEM. We have seen the construction of a TEM. We have seen the working of a TEM. After that, we have started discussing the scanning electron microscope. We have seen the schematic diagram of the SEM. We have seen the construction of the SEM. We have also seen the working of the SEM. Thank you.